text that I know of that derives two-dimensional symmetries. And so what I will give you instead is a set of notes, nothing fancy, just handwritten, but which will carry out each of the derivations in detail. So you'll have something to fall back on if it seems overly complicated. Any questions on what we've done to this point? We've really set forth the ground rules and components of our final step. And that, as I mentioned earlier, is to combine these collections, one or more of these collections of symmetry elements around a fixed point in space with one of the 5 two-dimensional lattices that can accommodate them. And when we find a successful, feasible combination, we will have derived something that we could call the two-dimensional crystallographic space groups. These are collections of operations which really pick up everything, the whole space, move it, tumble it end over end, and throw it back down into coincidence with itself. So hence the term space group rather than point group, where it's only a point that's left invariant at worst. Okay, so what we're going to do then is to take each of the point groups in turn and combine each of them, when possible, with one of the 5 lattice types. And I remind you that those are the oblique lattice or parallelogram lattice. And this was what was required by 2 and 1, no symmetry at all. Then there was the rectangular net, the primitive rectangular net. And the symmetry element that required that was a mirror plane, or we could have, depending on how the mirror plane was aligned relative to the translation, we could also have a lattice that was non-primitive, a double cell, and that was a centered rectangular net. And neither of those was compatible with the mirror plane. Then we had a square cell, square net or square cell, and that was what was required by a 4-fold axis, and then the hexagonal net, and that could be required by either a 3-fold or a 6-fold. Well, if you add up the number of point groups that we've listed here, there are only 6, but there are 10 crystallographic point groups. So what about the ones that we have not yet considered adding to a lattice? And these are the nets of the form CNV. So let's consider in turn each of those point groups and see what they would require of the lattice that could accommodate them. Well, let's do 2mm first. 2mm, the 2 is compatible with an oblique net. The mirror plane wants either a rectangular net or a centered rectangular net. So all we can do is to add this to a rectangular or centered rectangular net. Let's put a 2-fold axis at the lattice point. The mirror plane has to be aligned along the edge of a rectangular net. If there are 2 of them, you just put one along each of the edges of the rectangular net. Okay? A mirror plane in a net could either go in like this or could go, for the center net, in like this. So what we're saying, 2-fold doesn't care, add a mirror plane. It means that the parallelogram has to become a rectangle. You can put the 2 mirror planes of 2mm in along the 2 edges of the rectangle, or do this equally well with a centered rectangular net. Put the mirror plane in parallel to the edges, just like we did in CM. Put the 2-fold axis in at the lattice points. So there's a lattice point at the corner, and there's also a lattice point in the middle of the cell. So for the rectangular net, we could put in either m or 2mm in both of these rectangular nets, the primitive and the centered. Fourfold axis requires that the net become still more specialized and have the shape of a square.
Just because you can't see on this
Oh,
side.
I'm sorry. I'll pace back and forth, which I usually do, then everybody will get equal time. Okay, so I'm glad you spoke up. Fourfold axis requires a square net. There are two mirror planes 45 degrees apart, and those mirror planes have to be along the edges of a rectangular net. Put one of them in this orientation, and that surely is along the edge of a rectangular net, along the edge of a net that's not only rectangular but square, but it has a higher symmetry, and that's fine. Looks as though this diagonal mirror plane might cause troubles, but let's note that if we look at the diagonal translations in this lattice, that they will define a centered rectangular net. So putting the other mirror plane in this way puts it along the edge of a centered rectangular net. So this mirror plane is perfectly happy as well. So in the square lattice, we could plop either symmetry 4 or 4mm. Threefold is an interesting one. That's the odd symmetry that does strange things. Here is a hexagonal net, and that's what a threefold axis requires. Okay? Two translations identical in magnitude and in terms of what goes on along them, and exactly 120 degrees apart. Now, I don't readily see any rectangle along the edge of which I could align the mirror plane in 3M. But it's the oblique shape of this net that throws you off. Let's notice that if I draw several unit cells side by side, that here is a double cell that has a rectangular shape. Okay? Take 2T1 plus T2 as one edge of the cell and leave the other one as T2, and we have defined a cell where that is identically a 90-degree angle. So one of the mirror planes of 3M could go in this orientation, and the other one would be 30 degrees away. So this would be the orientation of the two mirror planes. So we're putting in 3M with M perpendicular to the translations that define the primitive hexagonal cell, T1 and T2. But there's another way you can do it. Let me draw the same net, the same hexagonal net, and look at a different kind of double cell. Okay, here is my hexagonal net. Two translations, T1 and T2, with a threefold axis at the lattice point. And now I will again draw a couple of extra cells. Let's double T1, and let's double T2. And now let me point out that I can put in the mirror plane this way and along this way. And here is a double cell. And I can put the mirror plane along this direction and this direction. So this is crazy. This is the same lattice in the same point group, but there are two different ways I can align the point group in the lattice. I can put the mirror plane in such that it's perpendicular to a cell edge, or put the mirror plane in 30 degrees away from that orientation such that it is along the edge of a centered rectangular net. So I could add 3M as well with the mirror plane aligned parallel to the translations in the net. So lots of funny permutations here. Here I have one symmetry element, two different lattices that I can combine with it. Here I have one point group 3M, but two different ways in which I can set it relative to the edges of the cell. Yep?
Why are you putting two mirror planes in each of those figures when you really only can do one mirror plane?
Actually, I need, well, there are going to be a radiating sheaf of mirror lines coming out of that threefold axis. They're at an angle of 60 degrees. It has to be 60 degrees, and that is indeed what I have here. I've just drawn part of 3M, and if I draw the remaining mirror planes, they would do this. Okay, I think that's fairly intelligible. Another reason for notes is to draw these diagrams when they're reasonably complex. On a blackboard, when you're rushing to get through it, is something that's easier said than done, even though you may have done it a number of times. All right, so there is the job that we've laid out for ourselves. 5 lattices, 10 point groups, and we can drop each of the point groups into one or more of the lattices of the 5 that we have determined. As soon as we combine things, we're going to have the situation that we've encountered before. In general, if I have an operation number 1 that produces one transformation of coordinates and combine it with an operation number 2, which has another change of coordinates, there must automatically arise some third operation. And we can write it in terms of the language of operators by saying operation number 1 followed by operation number 2 is equivalent to an operation number 3. And in terms of the pattern, this says that whenever you throw 2 symmetry transformations together, a third one pops up. You can't push it down. It's going to be there once you add the first 2 combinations. You may have to be really clever to see where it is and what it is, but it's going to be there. It's going to be there. It comes in automatically. So this general class of statement, this equality in operations, is something that I like to call for short a combination theorem. And we've seen several examples of this already, notably the one in the last hour that said whenever you combine 2 mirror lines at an angle mu, you automatically create, like it or not, a rotation operation of A2 mu. So as soon as we start making these combinations, we're going to find a new operation arising. So let's start with the simplest one, add a one-fold axis to a general oblique net. So there is T1, there is T2. We don't put anything in it. It's just a simple array of translations with lattice points that we can put at the terminal point of these translations. There's no symmetry. If we put in one atom, that atom hangs on every lattice point. And that's all there is to it. It's so simple, it's not only uninteresting, it's ugly. It's just a simple atom arranged in a periodic array. As with everything we've done so far, it's convenient to have a notation to indicate which particular plane group one has. And the symbol here is to give side by side the type of lattice as the first part of the symbol, and then the point group that you have added. So what do we have here? We've taken a primitive oblique lattice, and we've added no symmetry at all, a one-fold axis. And here, people who have derived symmetry theory assume that the reader knows something. And so you're going to get a lot of respect when you show your colleagues that you know what this notation means. All you have to do, if you know the symmetry, is to state whether the lattice is primitive, as it has to be for an oblique net, or whether it's centered in the case of the rectangular net. 3 dimensions is a lot more complicated. If the lattice is cubic, it could be primitive, it could be face-centered, it could be body-centered. So you need a symbol that tells the type of lattice. In this case, it's primitive, and the point group that we've added is 1. So this rather boring, ugly thing here is called P1. Another bit of code. We're going to do eventually the same thing in 3 dimensions. We're going to take just a general oblique 3-dimensional lattice and not adorn it with any sort of symmetry at all. And that will also be called P1. But to distinguish the two, P1 means, capital P1 means a 3-dimensional lattice. And we won't be working with those for a while. We haven't even enumerated them. A lowercase p. That is a symbol for a 2-dimensional net. In other words, a plane group rather than a space group. So here's the first, P1, and really doesn't give shivers running up and down my spine to look at it. So let's do one that's a little more interesting. Let's take a 2-fold axis and combine it first with a primitive rectangular net. I'm sorry, what am I saying? I want an oblique net. So the symbol, and I'm assuming this is going to be unique, and we haven't seen anything with a 2-fold axis in it, so it is. So this would be P for a primitive lattice, 2 for the symmetry that you've added to the lattice. And since you are all cognoscenti, I don't have to tell you it's an oblique lattice, because you know, don't you, deep down in your heart, that a 2-fold axis requires only that the lattice be an oblique lattice. Nothing special is required. So what we will do is to take this general oblique lattice with 2 translations, T1 and T2. And to this, remember, we don't deal with symmetry elements. We have to do this operation by operation. So what we're doing is taking the operation a pi, the only non-trivial operation contained in a 2-fold axis, and putting that in at a lattice point. Okay. Bells ring and whistles go off. We don't know what happens when we make this combination. And let me do this in more general terms so we can derive a theorem once and for all. Here's a translation, and let me add to the end of that translation a rotation operation A alpha. In this case, it would be the operation A pi. What's the net result of rotating and then translating? That's a non-trivial question. So if I'm doing this for a general rotation of alpha, let me take a translation, and I'm going to make my construction in the following way, because I'm really clever. And I am going to put this translation T at 1/2 of alpha on one side of the perpendicular to T, and then I'll let that that rotation go to work, and it'll take the translation and move it to alpha over 2 on the other side of the perpendicular. And now I'll let the translation move this rotated translation, and if it does so, it's going to move the translation over to here. Okay, here's a motif hanging on this translation, gets rotated over to here, and then gets slid over to here. This one is right-handed, this one is right-handed, this one is right-handed. How do I get from this one to this one? Only two ways, translation or rotation. If we rotate, about what point are we rotating? Now I'm going to use a definition, which seemed trivial. I said a symmetry element is the locus of points that is unmoved by the operation. And if we've decided, because these two motifs are not parallel to one another and have the same chirality, that the rotation has to be a rotation that relates the two, if I ask finally the question, what point is left unmoved? It's this point where these two translations come together at a single point. That's the point that's left unmoved by rotating from here to here and then sliding over by the translation t. And I can say exactly where that rotation is. It's going to be along the perpendicular bisector of my original translation. And where is it going to be located? This line makes an angle of alpha over 2 with respect to the perpendicular to t. So that angle is also alpha over 2. This line and this line both make an angle of alpha over 2 relative to the normal to the translation. So this angle is also alpha over 2. And look how this has turned out. The combination of a rotation with a translation is another rotation, B, about a different point, but through the same net amount alpha as the original translation. On top of that, really to nail this down, where should we look? This distance in here is t over 2, and the cotangent of alpha, the tangent of alpha, is t over 2 over this distance x. And if I just solve for that distance, x is equal to t over 2. I'm sorry, I got this garbled. T over 2 over x is equal to the tangent of alpha. That's what I wanted to do. So if I solve for x, that distance x is t over 2 over the tangent of alpha, and I can write that as t over 2 times the cotangent of alpha over 2. Okay, so here it is done properly at last. Go up a distance x along the perpendicular bisector of t, and you go up a distance t over 2 times the cotangent of alpha over 2. So this is a general result for any rotation operation. Combine a rotation operation A alpha with a perpendicular translation, perpendicular to the rotation axis A. And the result is a new rotation operation through the same angle, but at a different location. It's at a distance x, which is equal to t over 2 times the cotangent of alpha over 2 along the perpendicular bisector of t. So this is a general theorem. This is a fact of two-dimensional life that is always going to be true regardless of alpha. And the only constraint is that the translation has to be added perpendicular to the locus of the rotation axis, and that has to be the case in 2 dimensions because the rotation axis has to always be normal to the space, the two-dimensional space. In 3 dimensions, we'll have to generalize this to make the translation have arbitrary orientation relative to the rotation axis, but we've got enough to chew on at the moment. Okay, yes?
We didn't denote the quantity x on
The distance x is the distance up along the perpendicular bisector. I'm sorry. I said it, but I didn't write it in. Okay. So let me go through it again, since we've got everything on the board. We start with the original object, rotate it by alpha, and then we further map it to a new location by the translation t. Both motifs are right-handed, but they're not parallel, so therefore they have to be related by a rotation. If we ask what is the locus about which this location has occurred, we use the fact that the locus of a rotation axis is the only point that's left unmoved by the net transformation, and the place where this translation intersects the translation that has been shifted over by t is a point that sits up along the perpendicular bisector of the translation by a distance t over 2 times the cotangent of alpha over 2. So that's in the abstract. Let's now look at a particular application of this to our addition of a twofold rotation to a translation. So here's the translation, t. We're going to put a twofold axis and the only operation which it possesses, namely a pi. And according to our theorem, up along the perpendicular bisector of t by a distance x equals t over 2 times the cotangent of alpha over 2 should be a new operation b pi. So in this case, this would be t over 2 times the cotangent of pi over 2. Cotangent of 90 degrees is 0. So this says that you go 0 of the way up along the perpendicular bisector, which means you stay right at the midpoint of t. So this says that if you rotate through 180 degrees, follow that by this translation, you should find that the net effect is a rotation of pi over 2 about this point. Boggles the mind, but let's show that it works. Okay, here is an initial point, initial motif. Number 1, and it is right-handed. We rotate by 180 degrees. Here's number 2. It stays right-handed. Then I pick it up and I move it by this translation, and it moves from here to here. Here's number 3. It stayed right-handed, and the way I get from 1 to 3 in one shot is to rotate 180 degrees about the midpoint of the translation. How about that? People are so astounded that they're stunned, except for the people who couldn't see what I was doing, and they're moving back and forth frantically trying to see what I wrote. Okay. Let you catch your breath, and then let's do this, use this to derive the two-dimensional space group, the plane group, that results when we add a twofold axis to an oblique net. And it's turned out very simply because if I've got the operation b pi here, that implies that I've got a twofold axis, because that's the only operation that exists within a twofold axis. So I'll start by putting in a twofold axis here. I'll combine a pi with this translation t1. I get a new rotation operation b pi in the middle of this translation. So there's a new twofold axis there. The twofold axis here hanging at this lattice point as well, and at these other lattice points. Combine the rotation a pi with this translation t2. I get a new operation b pi sitting in the middle of this translation. So I've got all I need to say that there's a twofold axis there. That twofold axis will get translated down here by t1. This twofold axis will be translated over to here by t2. And then the only other thing that I have to combine this translation with is the translation t1 plus t2. And that combined with a pi says I should have b pi in the middle of that translation as well. So I'll get another twofold axis in the middle of the cell. And that's it. We've got our first non-trivial two-dimensional space group. And what do we call this? Confusing as hell, some might say, but crystallographers would say that's a primitive lattice combined with a twofold axis. This is P2. I don't have to tell you that it's an oblique net because you know that that is all that a twofold axis requires, that the net be oblique. What does the pattern look like? I'll say another thing that's so simple it takes a while for it to sink in. The pattern of a plane group is the pattern that is generated by the point group merely hung at every lattice point in the net. So if this is what a twofold axis does, relates a pair of motifs like this, a pattern for P2 is this pair hung at every lattice point. So all of the objects are of the same chirality, all either left-handed or right-handed. I've got the same pair at every corner of the cell. And notice that these new symmetry elements that popped up, just like what we found in the point groups, the new mirror planes that came arose as a consequence of the combination that we had made, and they were independent in most cases, 3M being the one case where they weren't. These additional three twofold axes are independent twofold axes. They're different kinds of twofold axes than the ones at the corner. Not only are they not equivalent by translation, but they do different things relative to the motifs that are in the pattern. This twofold axis has a different relation relative to the two closest motifs than does this one, than does this one. They relate different objects pairwise in the pattern, and no two of these twofold axes describe the same pairwise relationship. So these are independent twofold axes. Independent in the sense that they do different things relative to the motifs in the pattern. Different in the sense that there is no other operation that throws this one into this one, and therefore of necessity would require that the pair about this twofold axis be the same as the pair about this twofold axis. Okay, so there is a first non-trivial two-dimensional space group. I should mention, probably an obvious fact, that this also has a cousin in 3 dimensions. If I just imagine all of these twofold axes extending out through space perpendicular to the plane of the blackboard, and take another translation that is also perpendicular to the blackboard, I would have the 3-dimensional space group, which has the same symbol except capital P, indicating that it's a space lattice. So almost at no extra charge, we've done all the work to determine one of the 3-dimensional space groups. Yes?
If we change the order of the combination of the translation and the rotation, do we get the same operation?
Okay, that is a good question. I really meant to mention it earlier in connection with the point groups. Does interchange of the order of the operations in a combination change the result, or change, in other words, the symmetry element that is equivalent to the net combination of the two? How many think yes? It does change.
Can you say that again?
Okay, if we have two operations, A and B, is operation A followed by B the same result as the operation B followed by A? Does the order make a difference? And how many say yes? The order does make a difference. How many say no? Well, this is one of these happy occasions where I can say, you're all right. Sometimes yes, sometimes no. So let's ask, when does it make a difference and when does it not? Let's look at one of our point groups. Let me take a non-trivial point group. This would be point group 4MM. Okay, so these are all mirror planes of two different kinds. And let me quickly sketch in the pattern. Pattern is just a pair of things hanging on the mirror plane, and that pair is rotated by 90 degrees. Okay, suppose we look at the operation a pi over 2, a 90-degree rotation in a counterclockwise direction, and let the other operation be sigma 1, this reflection plane here. Suppose we reflect and follow that by a pi over 2. We reflect to here, and then we rotate by 90 degrees, and that's going to give us number 3 sitting up here. So we reflected and then rotated. How about if we first rotate that same object by a pi over 2 and follow it by sigma 1. So we'll rotate number 1 to here. So this is 2 prime. And you can see we're already in trouble. If we now reflect along sigma 1, this is 3 prime. So in one case we ended up here. In the other case we ended up here. So the order did make a difference. Okay. Let us look at another example. Let's look at 2mm. So here's an operation sigma 1. Here's an operation sigma 2. So let's first do sigma 1 followed by a pi. So here's object 1. Reflect to here, and then we rotate by 180 degrees, and this is number 3. Now let's do the operation a pi and follow it by sigma 1. So we'll take number 1 and rotate it up to here. So here's number 1 prime, and then we reflect by sigma 1, and 3 prime are exactly the same. So it didn't make a difference. So the answer is sometimes yes, sometimes no, which is interesting, but even more interesting is how can you tell? Yeah, question.
In that first example you drew,
yep.
the right side, it seems like the columns are drawn backwards. That is in fact
could be.
Work.
No, they're these are drawn backwards. They should all have their tails pointing in. No, it doesn't work actually, because even if I screwed up on the orientation, the positions are different. Again, first time I reflected and then rotated. So this is 3. If I rotate and then reflect, I'm way over here. So this is one location, this is another location. And even if I screwed up by having the tails pointing in the wrong orientation, it's still not the same. But here, clearly, reflecting and rotating is the same as rotating and reflecting. I end up in the same place. So how can you tell? It's a very difficult thing to prove that this is the case, but you can interchange the order of operations when the two symmetry operations that are involved leave each other untransformed. And if the two symmetry operations move one another, then changing the order changes the net result. It doesn't change the nature of the operation, but it does change the locus about which it operates. Let me show you what I mean. Here's 2mm. The 2 forward axis takes this mirror plane, turns it upside down. It takes this mirror plane and flips it over. The mirror plane is left unchanged in both cases. The mirror plane has the twofold axis sitting right on it, so it doesn't change the location of the twofold axis when it acts on it. And similarly, this mirror plane takes this mirror plane and reflects it end to end. It doesn't change anything. So all of these operations, the 3 independent operations, sigma 1, sigma 2, and a pi, all leave the locus, their locus of operation unchanged. Whereas that clearly is not the same for a 4-fold axis in a mirror plane. The mirror plane, when it acts on the 4-fold axis, leaves it unchanged, but the 4-fold axis, when it acts on the mirror plane, moves it to a new, entirely different location. And when that is the case, the order does make a difference. Okay. So I can take that corny joke of the mathematicians, what is purple and commutes? An abelian grape. I can say, what is purple and commutes? It's a purple fourfold axis and a mirror purple and a mirror plane. A purple 4 Okay, one other aspect of plane groups and three-dimensional space groups is an analytic representation of the way the plane group maps atoms around. And I see that it is 5 of the hour, so let me just make one final statement to indicate what I'm going to talk about next time. Here's the arrangement of twofold axes. And if you have an atom sitting in here, and this is T1 and T2, and we use this as the basis of a coordinate system, so this atom sits at a location X along T1 and Y along T2. And then I ask, what other atoms are related to it? Well, that twofold axis will move X to minus X and move Y to minus Y. And those are the only 2 atoms I get. So a characteristic of this plane group, if I were describing to you a crystal structure which had this symmetry, I might say something like a lithium in a position with coordinates x, y, and therefore x and minus x minus y would also have to occur. I have an oxygen at a different number, x prime, y prime, and that must then also occur at minus x prime minus y prime. And it looks as though anytime you throw in an atom at a location x, y, you get a symmetry-related companion to it with negative the coordinates. And this is what is called the general position of the space group. There's nothing special about it, and you put in an atom here, you get another atom here. This is going to be a nice economical way of describing an atomic arrangement, particularly if you realize that there are almost 150 atoms that appear in the unit cell for some of the cubic symmetries. Drop in one, wow, all hell breaks loose, 150 other ones. Well, what you can do is codify the coordinates of all these symmetry-related atoms, and that is a great utility in describing crystal structures because I only have to give you the coordinates of one representative atom. But this is not the only thing that happens. This is the general position because it's general relative to its location with respect to the symmetry elements. If x and y were both 0, I would have one atom moving to the origin to coincide with the second one. And if I put one in at 0, 0, that's all I'm going to get. The twofold axis is just going to twirl it around, and the translation will repeat it to the other lattice points. So if I put in an atom at 0, 0, that's all I'm going to get. And the same thing would occur for any of these 4 independent twofold axes. If I let x and y migrate to 0, 1/2, this atom will join together with this atom, and I would get just one atom sitting there. So there is a position also of the form 0, 1/2, and a position 1/2, 0, and a position 1/2, 1/2 that are the location of these 4 distinct twofold axes. Okay, to have a shorthand way of referring to the general position and these positions which are called special positions. What's special about them is that they're right on top of a symmetry element. And whenever that happens, the number per cell is a submultiple of the number in the general position because coalescence has occurred. And so there are 3 independent twofold axes, so there are 4 locations where you get only 1 atom per cell rather than 2. And then to give you a way of referring to these positions readily, they are labeled starting with the most specialized, just going through the alphabet: position A, position B, position C, position D, position E, which is the general position. And then another piece of information that's almost trivial here, but is not for more complicated symmetries, this what's called the rank of the position. And that is the number that you get per cell. One per cell, and for the general position you get 2. So the rank of the position is just the number per cell. And then if it's a special position, the atom has to sit at a site of some symmetry, and in this case, the atoms all sit at twofold axes for the special position. The general position always has site symmetry 1 always. So that's the characteristics of the way in which this symmetry can move atoms around. And this is of great utility in interpreting structures. For example, suppose our motif was not an individual atom, but was a molecule. And suppose you had 1 molecule per cell. That would tell you the molecule has to fit in a special position. And the special positions are all twofold axes. So if the molecule has to sit on a twofold axis, the configuration of that molecule has to have at least a twofold symmetry, or else you can't fit in 1 per cell in this particular plane group. So you can use this information to determine structures. I'm going to give you a problem a little bit later on when we get to 3-dimensional crystallography, and I'm going to give you the cell edge, the magnitude of the cell edge, and the density of rock salt. And from that, in 10 minutes, you can find out that there is only 1 possible structure for rock salt. The Braggs fiddled around for the better part of a year doing X-ray experiments and trying to calculate what the intensities would be for different atomic positions. You, in another 2 weeks, can get the same answer in 10 minutes, knowing only the lattice constant and the density. And the space group. So a lot of physical consequences of the nature of the structure, the conformation of the molecule, the extent or absence of solid substitution of one species for another can be dredged out of the properties of the space group. Okay, I've run 2 minutes over, but we took our break 2 minutes later, so let's call it a day, and I shall see you on Thursday. Hopefully armed with pictures so I can personally present each one of you with your corrected problem sets.